Hey guys, welcome to this tutorial for Lamport's Logical Clock, a fundamental concept in distributed system. This helps us to reason about the order of events when there's no global clock. This idea was first introduced by Leslie Lamport in 1978. He's a renowned computer scientist and a Turing Award winner in his seminal paper Time, Clocks and the Order of Events in the Distributed System. In distributed systems like cloud services, microservices, or global banking networks, multiple servers run independently across different machines or locations. They communicate by sending messages, but they don't share a single perfectly synchronized physical clock. So to illustrate this problem, let's look at a distributed banking system. Imagine a customer's bank account is replicated across two servers. That is, one is server A and one is server B. So we can assume that the account has $100 in the beginning. Now the customer deposits $50 to an ATM which is near to server A. Simultaneously, the customer tries to withdraw $120 that is in from another ATM, but that ATM is near to server B. So without proper coordination, here's what's go wrong. We naively rely on physical timestamps. Suppose server A's clock is slightly ahead due to normal clock drift or skews. The deposit event on server A gets timestamped by 10:00:05. Sorry, 05. Okay. The withdrawal request of server B, for instance, get timestamped maybe 10:00:03. Now, when the servers try to reconcile or merge the log using these physical timestamp, it seems server B sees the withdrawal as happening before the deposit. It might allow the withdrawal, dropping the balance to around -$20, then apply the deposit later. So this leads to inconsistency. The system thinks the withdrawal happened first, violating the real causal order. The deposit should have been processed before the withdrawal could have been checked. Physical clocks are unreliable in distributed environments because of clock skew or network delay. We can't guarantee perfect synchronization across machines. This is exactly the problem Lamport's logical clocks solve. They don't try to measure the real time. Instead, they provide a way to partially order events based upon the causality, capturing the happens before relationship without needing synchronized physical clocks. Let's start on the deep discussion of happens before relationship. Now let's discuss how internally the Lamport logical clock works. We have two servers, server A and server B. Each of the server has a counter that is initialized to 0. These counters does not increment based upon the timestamp, but they increment based upon the events. So for instance, in a previous example, when we deposited $20 in the ATM which is near to server A, we will have an event. So when the event happens, the counter is incremented by 1 and the deposit amount is $20. Now the server A has to send that event to server B so that it can know that $20 has been deposited. In that case, when we need to send the message, the counter will be incremented by 2 and it will be sent to the server B. The message is plus $20. Now, the server B has received a message. Here there will be a change of event, but the formula is different in this case. So what will happen is we will increment the counter not by +1, but we will do max of t dash comma t plus 1. T dash is the counter received from the previous server, that is 2, and t is the counter of the current server, that is 0. So in this case, the max is 2 and plus 1, which is equal to 3. So the counter is now pointing towards 3 and that is plus $20. Now, another event happens that the same user withdrew $100 from the account. So, since the event is happening on the same server, there will be an increment of 1. So, it will be 4 minus $100. Now, in this case, server B needs to send a message to server A for reconciliation. So, how it will send? First, it will increase the counter by 1 of server B and then send the message to server A. In this case, now the counter will change. So the counter will become max of 5, 2, that is equal to 5 and plus 1. So this will be 6. So now the counter will be at 6 and the message will be minus $100. So this is how the Lamport logical clock happens. There is one minor thing which I wanted to tell you, how we make the structure of the time clock. So essentially what we need to do is, along with the counter, we also need to mention the server name. So usually the syntax is like 0, A, 1, A, 2, A, similarly 6, A. Now on server B, it will be 0, B, 3, B, 4, B, and 5, B. This is how internally it works. So let me revisit the algorithm. Okay, so the first line says that for local internal event, increment the processor's key by 1. So we did the same. It means in the same server, it increments the process clock by 1. Then the second event is sending a message. So in sending message, first we increment the sender's clock by 1, then assign the new clock value to the sent value, and then include the current clock value in the message payload. The third event is receiving a message. So we update the receiver's clock to max of local time, M, where M is the counter received from the previous server plus 1, and then assign new value to the received event. So Lamport's logical clock are a brilliant way for capturing the causal order. They guarantee that if event A happens before event B, then the timestamp of A is strictly less than B. But they are not perfect. If two events have to happen at the same time, then we cannot conclude they are concurrent. So the Lamport clock might mark it as a different timestamp or mark it as a same timestamp. So Lamport clock basically fails if the events are concurrent. So it cannot decide that one of the events happened before other. So for this, there is another method by which we can find out and differentiate the causality of concurrent event. That is solved by vector logical clock. So the vector logical clock helps us solve this. In the next tutorial, we will work on vector logical clock, where we will solve the problem where a concurrent event has happened and we want to find the causality. Till then, see you in the next video. Bye.